So hi everyone, this is the first class in our online course on Combinatorics 2 at Stockholm University. And so today we will talk about basic principles of counting. So this is the material covered in 1.1 up to 1.4, so chapter 1 of the book. And most of this stuff you should have seen already in previous courses. Okay, so what the book does, it starts out with rules of sum and product. So and this is really easy. Namely, think about the following situation. You have 3 black shirts, 4 white shirts, and 5 red shirts. So, situation following, you have like 3 black shirts, 4 white shirts, and 5 red shirts. So, how many ways can you choose a shirt? Let's make a break here. Okay, you thought about this? Well, of course, we have, in total, we have 3 plus 4 plus 5 many choices to choose a shirt. So this absolutely simple observation is called the rule of sum. Now let's make it a little bit more complicated. So now in the morning you have to choose, so let me think. Okay, so you have to choose shoes. So you have, let's say, 5 shoes. And to make this look the same, let's write it in the same order. So let's say we have, in this case, 3 shirts. We have 4 socks. And we have 5 shoes. Okay, so deep mathematics going on here. Now the choice is, how many choices of outfits can you make? Well, you can choose one. You have to choose 1 shirt, 1 sock, and 1 shoe. So we can choose three possible choices here. For each such choice, we now have 4 possible choices, and then we have 5 possible choices. So in total, we get 3 times 4 times 5. And so these are the possible choices. And this is called the rule of product. And of course, you see the simple reason is here that these are independent choices. So therefore, you just multiply these numbers. And that's it. That's already the first section. Okay, so let's go to something more interesting, to sections 1.2 up to 1.4. So what we do here is we recall, so I think you should know this before. I hope you've seen this before. If not, really carefully read through the sections in the book. So here we think about the most basic of counting problems. Namely, you have n distinct objects, and you choose them r times. And if you think about it, of course, it depends now what is really the question. So whenever you ask about how many ways are there, or then you have to make very precise what you really mean by this. And so the first important thing here is, and I really wrote it very clearly here, these are distinct objects. So these are numbered objects, or these are people, so clearly distinguishable. So this is the important thing here. And so now we have different choices. We can do it without repetition, with repetition. We can, maybe the order is very important, or maybe the order doesn't matter at all. And so we see all these numbers, all these formulas here, and these notions. And so this is like a summary of what's going on in the section. So what we want to do now is we look at some examples. And I call it the small table. I just say why, because later on, we won't actually talk about all the cases, but it will be a much bigger table of choices. And so therefore, this is like the basic thing, so you should know all of this by heart. And so we will talk about this in the following order. So this is the first example, second, third, and the fourth. Okay, so start with number 1. Arrangements. Arrangements. Okay, so the word arrangement always denotes that the order is important. Okay, so this is the important thing about arrangements. Order matters. So, typical example, question. Let's say using ABC. So here's the question: how many words of length 5 can you make? And if you by just using the letters A, B, or C. So, well, the important thing here is a word. So word means the order is important. A word is a certain order, and so this means we should look for this column. The second thing is it tells you can use letters, maybe several of them. So this means like repetitions are allowed, so we are down here. And so what's the answer? Well, without looking at the formula, you of course can solve this problem. For the first position of your word, you have 3 possible choices. Now then for the second position, you have 3 possible choices. And we know, well, this is a rule of product, that we just multiply them. So we get this. And this is the answer. Okay, and so in this case, what is n? Well, we have 3 distinct objects, A, B, or C. So n is 3, and we choose them 5 times, so r is equal to 5, and so we get 3 to the 5. Okay, so this was easy, so let's go to the second. Okay, so this is about this spot in the table, so permutations. Now, what is this? Well, typical example is the following. So assume you have like six books, and you want to put them all on the shelf. And how many ways can you do this? Well, if you think about it, what we do is, well, we always choose for the first position one of the 6 books. Then comes the second position. And there we only have like 5 books left, and so forth. And so this is a typical scenario where this occurs. And so I also call them rearrangements, because think about that you already have the 6th book on the shelf, and you can ask, how many ways can you rearrange them? Well, this is the same question. So let's phrase a slightly different question here. How many lists of first, second, third winners in a competition with 7 participants Well, we need a verb in that sentence, so I guess are possible. Okay, so how many lists? So if you have a competition, there are 7 participants. How many lists can you get of winners? Well, of course, it matters if you have first, second, or third place. So think about it a second. Well, without even thinking about this table, of course, it's easy to answer this question. Well, for the first position, we have 7 choices. For the second, we only have now 6 left. And for the third one, we have only 5 positions, possible participants left. So this is the same as 7 factorial over 4 divided by 4 factorial. And now, of course, if you look here, this is precisely the case that n is 7 and r is 3. And now this is what we do. We have 7 we have 7 participants and we choose them 3 times where the order is important, but repetitions are not allowed because, well, people are different, they only exist once. Okay, so for number 3, let's just change a little bit the question. I want to ask how many groups of winners in a competition with 7 participants are possible. So what does this mean? It means like that if we know that person A, B was first place, B was second place, and C was third place. Now if we have maybe person C is now the first place, and maybe person B is now third place, and whatever, C is second place. So it doesn't matter. We only look at we would only publish them as them in a group. You would say that A, B, C won. So how many possible winners do we have? So think again about this. Okay, so let's first, what is the complicated thing here is that we do not, so here the order is not important. Okay, so before the order was important, so we were choosing these 3 positions in a certain, so there were like 3 positions, so we're choosing in an order, but now somehow the order does not matter. So the things like how I phrased it here is that I said that only the outcome is important. Only the outcome. You choose 3 times out of 7 participants where repetition is not allowed. You cannot choose the same person twice, it only wins once. But only the outcome is important. It doesn't matter which way you choose. And so we know what the answer is. The answer should be 7 over 3. Now, if you forgot about this formula, where this comes from, how can you see this? Well, think about what we had before. The answer before was 7 factorial over 4 factorial. So these were all the possible lists, so with a certain order. So maybe A, B, C. But now if we, among all of these, there's also a possibility of A, C, B. There's a possibility of B, A, C, B, C, A, and C, A, B, C, B, A. And so there are 6 lists which give you the same outcome. And so that means we have to divide all this big number of lists, we have to divide them because many of these lists just give you the same outcome. So we divide by 3 factorial. By all the possible permutations. And that is precisely 7 over 3. And this is also how you prove this formula. So a different way of thinking about this is that you have these 7 participants. Think about them as being elements of a set. And you choose the group of winners. So these are 3 people. So you choose a group of 3 people out of them. How many possibilities do we have? Well, this is precisely the number of subsets of size 3 in a set of size 7. So this is a different interpretation. So what I want you to do is, if you forgot about this, is to definitely read again about the importance of a binomial coefficient in the binomial theorem. So please read about the binomial theorem in the book. So this is in section 1.3. And it would be also nice if you also would actually try to read about multinomial theorem, so about multinomial coefficients. This is a generalization you also might have seen before. It's not that important for this class, but it's definitely good to know. Okay, so this brings us to number 4. So number 4 is somehow the one where usually one cannot remember the formula. And somehow this is something that you always associate with that it's very complicated. But somehow it's also the one thing which really turns up in lots and lots of examples. So this is very important. And so, of course, you can think about lots of examples where you choose where only the outcome is important, and you also allow repetitions. So typically, so in what's important for also the rest of the course, there are kind of two scenarios you should definitely know about. So here's the first one. Put 5 identical balls into 3 labeled boxes, namely A, B, and C. How many possible outcomes? Okay, again, think a little bit about it. So one thing here is that you might be, well, a little bit confused. Why? Because in this table, I stressed quite strongly that this should all be distinct objects. Now suddenly, we hear about identical balls, so balls which you cannot distinguish. So something, how does this fit into that, in this kind of setting? Well, what I claim is the following. I claim this is the same as choosing 5 times out of the set of 3 elements A, B, C, where order, so this means without, so where order is not important, and this means with repetition, so repetition is allowed. When you think about it, well, that's precisely what this is. You have these 3 boxes, and you have this, 5 balls, and now you choose for each of the balls, you choose one of the 3 boxes. And of course, you can choose for them several times. So for the second ball, you might choose the same one again, so therefore with repetition. But the order is not important. It doesn't matter afterwards. Well, if you first choose the first ball, maybe the first ball, the box A, or with the second ball, the box A, only the outcome. Just at the end, if someone comes through the door and looks at the boxes with the balls in there, that's when you decide what the outcome is. So the order is not important. And that means that in this case, well, n is equal to 3, r is equal to 5, so the formula tells us that the answer is 7/5, namely 3 plus 5 minus 1, 8 minus 1, 7 over r is 5, so 7/5. Well, this of course is easier to compute as 7/2. And let me just write again. It's good to know that you can always think about this in general. So n plus r minus 1 over r is the same as n plus r minus 1 over n minus 1, just as an aside. Okay, and of course this number is easy to compute. Yeah, very easy. Okay, so the good thing about this way of thinking is also that it explains this formula in a nice way. Why? Because think about this example. You have these 5 balls. You want to put them into 3 boxes. So for instance, you can put them like this. Maybe in the first box, the box A, there are 3 balls. In the second box, maybe there's 1 ball. And in the last box, there's also 1 ball. Now maybe something else. Maybe in the first box, there are 2 balls. In the second box, maybe there are 2 balls. And in the last box, maybe there's 1 ball. So clearly, you can write down all the outcomes in this way. Now, if you think about it, what do we have? We have 1 plus 1, 2, 3, 4, 5, 6, 7 symbols where we choose 2 of them to be very special. Namely, to be not dots, but dashes, if you like. So that's what you do. You take these 7 symbols and you choose 2 of them to be special, like this. If you think about it, in all these possible ways, you get all the possible outcomes. So this is something kind of magically, and that's precisely what we do here. 7 out of 2, that's the answer. So you choose 2 special elements out of 7. And in the same way, if you read about it again, maybe a little more slowly, you can prove this formula if you've never seen this before. Okay, so here's the second scenario. A typical question where, which belongs to this setting is following question. What's the number of solutions of the following equation? X plus y plus z is equal to 10. So I often I write one just like this without writing it like this. So I hope this doesn't confuse people. So 4 x, y, z. In this, what does this mean? Well, these are all the integers greater or equal than 0. So often this is just, you can think about the natural numbers. Okay, so we think about, we have to solve this problem. So how do you do this? Well, I claim, of course, we know already what the answer is. So let me just write following. Okay. So I claim that this is the same as putting 10 identical balls in 3 boxes labeled X, Y, and Z. So why is this? Well, you have this, if you have a solution here, maybe how does the solution look like? Maybe the solution is 4, 3, and 3. Well, you can just think about it as being like 4 balls sitting in box A, 3 like box X, 3 balls sitting in box Y, and 3 balls sitting in box Z. And now that's precisely, now all the solutions you can think about them in this way. So where you put 10 identical balls in these 3 boxes and you just look at the outcome, and that's the solution in this way. And of course it's also possible that maybe you have like 9, 1, 0. That would mean like there's no ball in the last box, only in the first 2 boxes. And so we can answer this question now. The answer is, well, just use the formula. So we have n is equal to 3, r is equal to 10. So this is, well, n plus r minus 1 over r. So 3 plus 10 minus 1 over 10, which is 12 over 10, which is, of course, the same as 12 over 2. Okay, so I have a little homework here. So the homework is what if no of these boxes should be empty? So what if X, Y, and Z have to be bigger than 0? How many possibilities are there? I will write the answer on the homepage. Okay, so here's the last. So the last little topic here of today, and I call it a special topic, namely because it somehow doesn't really maybe while the previous example maybe looked as it didn't fit in there, but we found out it fit perfectly in there, the one about the identical balls. Now this one here really is slightly different. So this is arrangements with non-distinct symbols. So non-distinct means that there might be symbols which actually are just the same. So here's a typical example. How many words can be made, using the following letters, and really think about them as being like Scrabble letters. Meaning, you really have them in front of you sitting there, like there's one of these little pieces, another of these little pieces. And so this is like A. So think about them in this way if you like. So this is a question, like you have these Scrabble letters like in front of you, and now how many possible words can you form? So what kind of should be a little bit of problem here is like, you see like this A and this A, for instance. I mean, they look the same. They're just the same. You can't distinguish them. So you cannot just like use this table. So how do you do this? Well, you use the same trick you've seen before. The way we think about it now is to think as if all of them would be distinct. So what would be the answer if all of these would be distinct? So if you could distinct this A with that A, so like this is A1, this is A2, this is B1, B2, this is C1, C2, and here's A3. So these are all really now distinct. Then the answer is easy, because now we have all these distinct letters. Think about the book example, like all these distinct books, and now in how many ways can you rearrange them? Well, of course, in 7 factorial. But now they are not distinct. So what do you do? Well, assume that you just look at these. Let's say just look at these two B's. Well, we have like these 7 factorial different permutations. And among them, maybe you have one there B1 is here and B2 is there, and everything else is just like, one example. But now maybe everything else just stays fixed, but these two gets exchanged. Then just looking at it, you would still from very far away, if you wouldn't see the little 1s and 2s, you would just think there's still 2 B's here. In other words, if you just change them, we have 2 examples among these 7 factorial which give you the same outcome, which give you the same word. So what you do is you divide by it. Divide by 2 factorial. And now think about the A's. The same thing happens here. I mean, we have 3 A's, and we can permute them in 3 factorial ways. And all of these different A's will give you the same outcome, will give you the same word. So we divide by it. And finally, we have 2 C's, so we divide by 2 factorial. And this is actually a multinomial coefficient. And this is how you solve this problem. And many, many problems which just look the same. And so this was the last thing I wanted to say, but one more thing, I don't let you go before I write this down, so let me write this up here. So look at the following problems in the book. So the most important thing about the book, so there's lots of theory in there. The theory is sometimes maybe a little bit complicated, like written down, especially like the proofs, but the examples are great. So have a look at the examples. Okay, so these are now the examples. So example 1.13, 1.15, 1.16. And I know this looks like a lot, but I mean, there are many, many, many more examples in the book. Also interesting, but these are the ones I especially recommend. So see you next week.